As we progress through Chapter 1, we will review bonding and look more closely at the kind of bonds that carbon likes to form. We can think of bonding as a continuum of sorts. When electron density is shared completely equally between two atoms, we say that the bond is nonpolar and covalent in nature. This type of bond occurs when the two atoms are very similar in electronegativity. Think of this in terms of a tug-of-war match. If both sides of the rope, electrons in our case, are being pulled with equal force, there's no net force in one direction or another. For a bond, this would mean that the electron density would be shared completely equally between the two nuclei. An example of this type of bond is H2, or elemental hydrogen. There's zero difference in electronegativity between two hydrogen atoms. Therefore, the electron density is shared equally between the two. On the other end of our bonding continuum is what we call an ionic bond, in which the two atoms involved in the bond are not sharing electron density, but rather one atom is so much more electronegative than another atom that it actually takes an electron from the less electronegative atom. The atom that gains the electron becomes negatively charged, or an anion, while the atom that loses the electron becomes positively charged, or a cation. An example of this type of bond is NaCl, or sodium chloride, where chlorine has removed an electron from sodium. The difference in electronegativity between sodium and chlorine is 2.23 using the Pauling scale. The two ions are held together by a very strong electrostatic attraction. To recap, we have nonpolar covalent bonds at one end of our continuum and ionic bonds at the other end. So what about all of the cases in between these two extremes of bonding? Bonds in which the electron density between two atoms is being shared, but not in an equal fashion, are called polar covalent bonds. In a polar covalent bond, one atom is pulling on the electrons more than the other because of a difference in electronegativity, but not enough to remove an electron. The result is the creation of a dipole, where one end of the bond assumes a partial negative charge, while the other end of the bond has a partial positive charge. An example of this type of bond is HCl. Chlorine is more electronegative than hydrogen, with a difference of about 0.96 on Pauling scale. So there is a dipole created in the electron density between the two atoms. The electron density around the chlorine is higher than that around the hydrogen. Most bonds that we will study, particularly in first semester organic chem, fall into the very broad category of polar covalent bonds. To give you some idea of the range of bond polarities that we will encounter frequently this semester, let's look at a few examples of some organic bonds, i.e. bonds to carbon. Obviously, a carbon-carbon bond will have no polar character, as the difference in electronegativity, delta En, is 0. A carbon-hydrogen bond has a delta En of 0.35. A carbon-nitrogen bond has a delta En of 0.49. Carbon-chlorine bond has a delta En of 0.61. And one of the more polar bonds we will study, a carbon-oxygen bond, has a delta En of 0.89. For this class, we will consider any carbon-carbon or carbon-hydrogen bond to be nonpolar. Yes, I know that the delta En for the carbon-hydrogen bond is not 0, but by treating the bond as not significantly polar, we are able to accurately predict the physical and chemical behavior of such bonds. In second semester organic, we will sometimes see bonds that approach the ionic end of the continuum. Bonds between carbon and various metals can fall into this region. Finally, notice that in all of the polar bonds that I gave as examples, that the bond dipole is pointing away from carbon, leaving the carbon atom with a partial positive charge. This arrangement of the bond dipole will be common in most of the molecules that we will study in first semester. The fact that carbon is often at the positive end of a dipole will have dramatic implications on the physical properties and chemical reactions we will study this semester.